back to another video for Math 2419, Calculus 2. Today we'll be talking about the gradient vector and its different applications. So we're going to start off by talking again by partial derivatives and what we had from last time. So again, you can recall that if we have some function, and again now we're dealing with functions of more than one variable. So if you have a function that looks like z equals to f of xy, what we could do is we could define its partial derivatives. So we can find what we said, f sub x at a point xy, or f sub y at a point xy. And again, the whole concept here was, now we have more than one variable, and so when we take a derivative of a function like this, you have to specify with which variable we're taking the derivative with respect to. So again, these are our partial derivatives. And again, the first one is the partial derivative of f with respect to x. The second one is a partial derivative of f with respect to y. And so we can, do these operations and get the information about the partial derivatives. Maybe we can ask ourselves a question: is there a way for us to kind of understand all of the information about all of the derivatives of this function? Maybe since we have the partial derivative of f with respect to x and partial derivative of f with respect to y, maybe we can put both of those in a vector, and maybe that would have some special importance to us. And it turns out it does, and so what we're going to do is define the first thing for today, which is going to be the gradient vector. And I'm just going to define it for the case of two variables. And so the gradient vector is, so the way we notate it is with this upside down triangle. Kind of looks like a Dorito, which we call nabla. It's not commonly called that, but just so you know, we just say nabla, or more commonly the gradient of f. And the way we define that is we have a vector whose first component, actually let me backtrack just a second. I want to evaluate this gradient vector at a specific point, x naught, y naught. So what this is going to be is a vector whose first entry is going to be the derivative of my function. Well, if it's the first entry, hopefully it's going to be with respect to x. I'm going to evaluate this at a certain point. And same thing for y, partial derivative of f with respect to y. And of course, the partial derivative of a function with respect to any of its variables is itself going to be a function. And so for both these component functions, we have to evaluate them at the specific point, x naught, y naught. So we have that here for the partial derivative of f with respect to x, and now here with the partial derivative of f with respect to y. Alright, this is our first important definition of the day. And what you'll see is that the function has input, like our function f, its input is two real numbers x and y, so it goes from r2, and it outputs some number z, so we get one real number r. If you remember when I talked about functional signature from the last video. But my gradient, they have the same inputs, right? They have two inputs x and y, or in this case I have specifically x naught and y naught. But my output is going to be a vector, in particular a vector in two-dimensional space. So I'm going to get r2. So this is something to note that's different between our original function and the gradient function. Okay, let's go ahead and practice by taking the gradient of a specific function, and then we will go from there. Okay, so we're going to find the gradient of the function f of xy equals 4y to the fifth divided by x. Okay, so for a question like this, it might help us to write our function as the product of these different terms. So what I mean by that is having 4x to the minus 1, y to the 5, just to make it easier for when we take our derivatives. Okay, so what we need to do is evaluate the partial derivative of f with respect to x, in which case we would get, well, bring the negative 1 exponent down, we get negative 4x to the negative 2, y to the power of 5. And the derivative of f with respect to y is going to be, the 5 is going to come down and multiply the 4, give me a 20. This x stays the same, x to the minus 1. Now y's exponent will decrease by 1. So we get y to the 4. So we conclude that the gradient of f at any point xy will equal, the first component is going to be f sub x at the point xy. The second one is going to be partial derivative of f with respect to y at the point xy. And so we get, carrying these two down, plugging them in, what we get is negative 4x to the minus 2, y to the 5th, and then 20x to the minus 1, y power 4. So that's going to be our answer for this first, more computational practice problem. Okay, so hopefully that makes sense. And again, for this class, we're only going to be really dealing with functions of 2 variables when we deal with multivariable functions. You could have more than that. You could have as many variables as you want, in which case your gradient, like let's say you have a function of n variables, and your gradient is going to be a vector in Rn. It's going to have n entries in it. Okay, so an important application of the gradient vector is going to be in what we call the directional derivative. So I'm going to go ahead and define that, and then have a quick little conversation about what it means. So we're going to talk about now what we call the directional derivative. Okay, so as the name suggests, very obviously we're going to be taking a derivative of a function, but we have to look and try to get some information based off of what this directional part kind of means. And so what we're going to do is draw a nice little picture to get some intuition on sort of what's going on here. And I'll kind of walk through where the directional derivative comes from. So we're going to set up our system in R3, so x, y, and z. And what we're going to do is consider just some function, just to have something drawn. We're going to do something like this. So this is going to be the graph of some function, f of xy. And so what we're going to do is pause for a second and ask ourselves a couple questions. The first of which is going to be, what does it mean to take a partial derivative with respect to x? So if I take a partial derivative of a function with respect to x, or I suppose with respect to y, and there are many different ways to answer that. You know, if we take a partial derivative of f with respect to x, of course that means holding all other variables, in this case just y constant. But we can think about this in another way, and the way is going to be, when I take the partial derivative of f with respect to x, this is a derivative in what direction? In what, not wad, sorry, in what direction? And then we're going to look at also what is constant. So this is just a conceptual way for us to understand and hopefully motivate the idea of needing a directional derivative. So we'll get our table set up. Okay, so let's look at the partial derivative of f with respect to x, in which case we hold y to be a constant value. So I'm going to start drawing back on my graph here on the left, and what I'm going to do is draw a plane. So what I'm going to get is something like this. Hopefully this will make some sense to us. There we go. And so what I get when I do this, again, we've done this before, but in this instance, what I'm going to do is get a path along here, looking like this, and for which all the y components of each of these points are going to be constant. And so this is going to be, for example, my partial derivative of f with respect to x. And so we would say that the partial derivative of f with respect to x is in the direction of I, which is going to be the vector 1, 0. So if that didn't make any sense, just recall that the vector I is the standard basis vector pointing along the positive x direction with components 1, 0. And so we see that this is pointing in the positive x direction, which is exactly the direction that we move in when we want to find partial derivative of a function with respect to x. So hopefully that makes sense. Kind of just getting the idea of a vector associated with our derivative and just having an idea of a direction is going to be very helpful for us. Now, of course, when we do this derivative, our variable y is going to be constant. Now, if I take a partial derivative of f with respect to y, we can think about that, like a good way of conceptualizing this is taking a derivative in the direction of the j vector, which has components 0 and 1. It's going along the positive y-axis, in which case x is constant. So now we arrive at what we have as our directional derivative. And the way that we notate directional derivative is going to be a d subscript u of our function f. We typically put the vector notation on u. So what this means is this is the directional derivative of f in the direction of vector u. And so maybe, for example, u could be the vector, I'm not sure, 1, 1. Right? We see that this vector is going to be different than 1, 0 and 0, 1 that we have in the first two rows. And so this is all this is meaning is that we're taking a derivative. So if we look back to our picture on the left, we're not taking a derivative. Well, so with the partial derivative of f with respect to x, we're going primarily in this direction that I've just drawn. The partial derivative of f with respect to y, we're going primarily in this direction along the positive y-axis. What partial derivatives allow us to do is take derivatives in any direction, like this, or something like this. And so we need the concept of a direction vector to get us to the point of understanding directional derivatives. And so what we say, typically u is going to be a normal vector, so what we have is the directional derivative of u, the directional derivative of f in the direction of u is going to be a unit vector, u, components a and b. It can be any two real numbers. And then what's constant? Well, we don't necessarily know, right? We're not entirely sure. We'd have to be given the vector to figure this out. And this isn't even that important. More of just kind of an idea of understanding. The important part's going to be going on in this first column right here. So hopefully this makes sense. I'm not going to walk through a proof of this. If you want to, you can come into peer tutoring and have one of our tutors explain it to you. Otherwise, there are good visual animations online that will explain this. I'm simply going to give us the formula now for the directional derivative, and then we'll move on from there. So the formula for the directional derivative is, so again, the way that we notate it is going to be d subscript u vector of f. And what this will be is the gradient of f dotted with my vector u. So this is what we're going to take as our formula for the directional derivative. And we'll go ahead and do some computational practice just to kind of get an idea. And perhaps a better way of saying this, what you could also say is, this function f is going to be evaluated at some point, x naught, y naught. And so what we're going to get is the gradient of f at some point x naught, y naught, dotted with this vector u. Okay, and this should make sense, right? So this is what we call, right here, it's going to be our direction vector. So it tells us in what direction our derivative, tells us in which direction our derivative is in. And so what we're going to do is a practice problem just to kind of get this concept down. And of course, then we'll go from there. Okay. So what we're going to do is, I guess I'll write example. We're going to find the directional derivative of f evaluated at the point 2, 0, where f of xy, so now I have to give you the function, so we're going to get x times e to the xy plus y. So now we know the function. Let's think what else we need to know. Well, of course, since this is a directional derivative, we need a direction vector. So where this function is given, and the second piece of information, u excuse me, is the unit vector in the direction. So now I have to tell you what direction it's in. And I'll do it this way by giving you an angle. So the unit vector, so u is the unit vector in the direction of theta is equal to 2 pi over 3. Okay, so let's go ahead and read this one more time. So I was going to make sure that the question makes sense before we go on. So we're finding the directional derivative of the given function f at the point 2, 0 in the direction of the unit vector that makes an angle of 2 pi over 3 with a positive x-axis. And so let's think about what we need to be able to solve this. So we need a couple things. First, we need, the equation tells us that we're going to need the gradient of f at the point 2, 0. And we're also going to need the vector. We're going to need the components of this vector. We currently don't have it. We just know the angle that it makes with the positive x-axis. Okay. So what we're going to do to start this problem out is try to find the direction vector u. And so what we're going to do is recall something that we've used a lot before, hopefully, is the fact that sine squared of theta plus cosine squared of theta equals 1. And so what we want is a vector u that has components cosine theta and sine of theta. Right? The reason being is because we said that we want u to be a unit vector, right? And again, something's going to be a unit vector if its length is 1. And so if we take this vector that we just wrote u, and we take its length, what we get is square root of, and then what we're simply going to do is take the sum of the squares of the components. So cosine squared of theta plus sine squared of theta. But we just showed, or we just kind of recalled, I suppose, that this is equal to 1 on the inside. So we get 1. So, i.e., u is a unit vector. Okay, so we're pretty much done with finding the unit vector u. And so we'll put that right here. So we have that u is equal to, so cosine of theta, so cosine, again, the angle that we were given is 2 pi over 3. And the y component is going to be sine of that angle. So what we get, cosine 2 pi over 3 is going to be negative 1/2. And sine of 2 pi over 3 is going to be positive square root of 3 over 2. Okay, that's going to be good for this first part. And then what we'll do after that is simply find the gradient of f at the point 2, 0. And then stick it in here, then we'll put it together, and then we'll be done. So hopefully all this makes sense. I'll give us a little bit of space here just so we can look at this a little more easily. So again, all we've done so far is found one of the two pieces we need. We found the unit vector by considering something that gives us a unit vector, right? The sine squared plus cosine squared theta equals 1. And then plugged in the specific value of theta. Alright, so I'm going to scroll down a little bit so we can find our directional derivative. First thing we're going to do is find the partial derivatives of f with respect to both x and y. Okay, so what we had again is f of xy equals x times e to the xy plus y. And so the partial derivative evaluated at some point, xy, is going to be the partial derivative of f at the point xy, comma, partial derivative of f with respect to y at that point. So what we're going to get, partial derivative of f with respect to x, we're going to have to use product rule, because in the first term we have a product of two functions of x. So what we're going to get is the derivative of, so we're going to look here. So the derivative of x is 1 times e to the xy plus, then what we're going to have is x times the derivative of e to the xy with respect to x. So we get y times e to the xy. And then the partial derivative of the function f with respect to y is going to be x squared e to the xy plus 1. Cleaning this up, we get e to the xy factored out. We get 1 plus xy. And then after that we get, well, can't really do much here. We get x squared e to the xy plus 1. Okay, so going back up for a second, right, we want to evaluate the directional derivative at the point 2, 0. And so what we're going to do is take the gradient of f, evaluate it at 2, 0. What we get is e to the 2 times 0, 1 plus 2 times 0. Then we get 2 squared e to the 2 times 0 plus 1. And then what we get is, well, e to the 0 is going to be 1. We get 1 times 1, so we get 1 here. And then what we get here is 4 plus 1 is 5. So not that we really need to go all the way back up and plug it in here, but I suppose just to have it together, we get 1, 5 is the gradient of f at the point 2, 0. Okay, so this is a lot to look at. Again, let's kind of talk about what we just did. First thing we did was we found the unit vector that we wanted. Sometimes you're not going to be given the vector. I mean, sometimes you will be given the vector, you don't have to do any work. Sometimes you define it like we did here. So we found u, and then we put it in here. Then we found the second thing that we needed, the gradient of f at the point 2, 0. So first we take the gradient. So step 2, find the gradient of f. We get this function right here. And then we evaluated it at 2, 0 to get this vector right here. So we put that up here. Now I have both pieces of information, and we can solve this exercise. And so we want to find the directional derivative of f at this point in the direction of u. So we have these two vectors right here. Finding the directional derivative simply amounts to taking their dot product, which should make sense to us because when we take the dot product of two vectors, we get a number. And the derivative of a function evaluated at a point is just, again, just a number, right? That's something that we're used to, because the derivative just tells us a slope, so we should just get a number. So we finish this one off by looking at, so we get directional derivative of u, or sorry, of f, I keep saying that, in the direction of u at 2, 0 is going to be the gradient of f at this point, dotted with u. Again, this was the vector 1, 5, and this was the vector minus 1/2 square root of 3 over 2. So when we do this, we're going to multiply component-wise. We get 1 times negative 1/2 plus 5 times root 3 over 2. We get negative 1/2 plus 5/2 square root of 3. Or probably we'd like to write it more like 5 square root of 3 over 2. Okay, so that's going to be all for that question. Hopefully everything made sense there. Let's go ahead and look at kind of some interpretations or things that we can get from the directional derivative. Again, so this is just our first example. So we're going to go ahead and move on. I guess this always happens. Start writing so big later on. That's okay. Okay, so what we're going to do is recall from before that if we have two vectors, u and v, so let's go ahead and write them here, vector u and vector v, then when we take their dot product, we get this equation that u dot v is equal to magnitude of u times the magnitude of v times the cosine of the angle in between them, right? Angle in between them, of course, for this picture being this right here. And so what we're going to do is remember that the gradient is a vector, right? The gradient also, of course, this vector u, so these are vectors. Let me do this again. So gradient of f and u are vectors. And so we can apply them in this formula from above to get that the gradient of f dotted with u, which again is the directional derivative by definition, is going to be, with this formula, gradient of f in magnitude multiplied by the magnitude of u times the cosine of the angle in between them. And so we can think, well, what's going to simplify here? Well, we know that we take u to be a unit vector, so we know that its magnitude is going to be 1. So we don't need to write this in the product. So what we're going to get is simply the magnitude of f, the gradient of f times cosine of theta. And this is all going to be the directional derivative of u. So this is going to be kind of nice for us in terms of interpretation because, given the function f, its gradient is going to be determined, just based on what the function is. And so what we really have here is that this expression depends on theta, right? Theta is going to be a variable. It can be whatever we really want it to be, right? So this expression depends on what value theta takes on. It's our independent variable. And so what we get is this expression is going to be maximized when the cosine of theta is going to be equal to 1. Because we recall that cosine of theta, same thing for sine, but here cosine of theta is bounded between -1 and 1. And so what we get is if cosine of theta is equal to 1, then this means that the directional derivative of f in the direction of u is this right here, which is when it achieves a maximum value. So all of this is to say the maximum value of the directional derivative is going to be the magnitude of the gradient. So I'm going to scroll down just a little bit. And so let's think about when this happens, right? So we're going to look at vectors. We're going to look at the vectors that are the gradient of f in u, and look at what happens when the cosine of theta is equal to 1. Cosine of the angle between them is 1. So what we have is, in this case, well, if the angle between them is 1, then we know that, if the cosine of the angle between them is 1, then we know that that angle has to be 0. So they're actually lying along the same line. So what we have is our vector u here, and our direction vector gradient of f here. And they're going along the same line, so there's no angle between them. And so in this instance, what we have is that the directional derivative has achieved its maximum. Okay, so that's very important to know. This will definitely come up, and we'll actually see it in the question here in a second. This is our first example. And then, well, when is the directional derivative going to be at its minimum? We go back to this equation right here. We see that it's going to achieve a minimum when cosine of theta is equal to -1, when it's at its minimum. And so, in the second instance, we're going to look at cosine of theta is equal to -1, which means that the directional derivative is equal to minus the magnitude of the gradient. This is when it's achieved its minimum value. So we have this, the maximum value, the minimum value is just the negative. So they're negatives of each other. And of course, this is going to happen when these vectors are at an angle of pi radians, 180 degrees from each other. Because of course, that would be when the cosine of the angle between them is going to be -1. And so we get is something like this. We're going to get u, and then the gradient of f. This is going to be the case of the minimum value. Again, that's the minimum of the directional derivative. Okay, so just to briefly summarize this, what we get is, so we get that the directional derivative is bounded between the magnitude of the gradient from above and the negative magnitude of the gradient from below. So this is a very succinct way of summarizing what we just said. It tells you when this achieves its maximum and its minimum. Okay, so what this means for us in application is we can look at when the gradient, because the gradient tells us like a direction, right? Because it's a vector, so it has direction associated to it. And so it's going to tell us, in particular, what our directions of maximum ascent and descent are. So let's talk about maximum ascent and descent. So the way I like to think about this is imagine that you are skiing, right? Or just otherwise on some hill. And I ask you, what direction do I have to walk along to reach the top of the hill the fastest, right? So it turns out the direction that you would have to follow is that of the gradient vector. And so what I'm trying to say is that, let's get a different color here. So if the unit vector and the gradient of f are, so look at two cases, if they're in the same direction, if these are in the same direction, then what we have is that we are going in the direction of maximum ascent. And of course, it should make sense that, if I'm at some point along the hill, and one direction will take me to the hill the fastest, then the opposite direction one that's 180 degrees from it will be the one of maximum descent. That'll get you to the bottom of the hill the quickest. So that is to say, if the vector u and the gradient of f are in opposing, or sometimes what we call anti-parallel, so parallel but in opposing directions. So if they are in opposing directions, what we get is that going along this direction will be that of maximum descent. Okay, so let's look at an example to hopefully clarify any possible doubts that might be lingering. So I'll scroll down. So what we're going to do is look at a question, and that question is going to be as follows. Let the function f xy be equal to x squared plus 2x plus 2y squared plus 4y. So now, so this is going to be the graph, and if you want to, you can graph this in some graphing software online. It's really helpful to get a visual, I think. Excuse me. So what we're going to do is locate ourselves at the point P, which has coordinates 1, minus 2. And so at this point, what I'm going to do is find the direction. So find the direction and value of two things. First off, greatest descent, and 2, that of greatest descent. Okay, let's go ahead and read this again. So we have a function, 2 variables, and we're at a specific point xy in the xy plane. So when we graph that point, we'll be at some height z on the graph. And at this point, we want to find the direction that we have to go in. That will be that of greatest ascent and greatest descent. But what we want is, I think I wrote this question. No. I wrote it right. Okay, good. Sorry, thought I messed up. So to find the direction of greatest ascent and descent, what we're going to do is as follows. So the direction, so let's look at part 1, we're looking at the greatest descent. And so the direction of greatest descent, well, we know from above, if I scroll back up for a second, that the information about greatest descent is going to be when u and f are in the same direction, which means that we have something like this, in which case the directional derivative is just the magnitude of the gradient. So what I mean to say is that the direction of greatest descent at this point, again, the direction is going to be a vector, so we need a vector. So it's simply going to be the gradient of f at the point 1, negative 2. And what I mean by value of greatest ascent is simply going to be the length of that vector. That is the magnitude of the gradient evaluated at this point. In part 2, when we're looking at greatest descent, what we're going to do is simply take the negatives of these. So the direction of greatest descent is going to be the opposite of what we had in 1, so the negative gradient of f at the point 1 minus 2. And the value is going to be, same thing, is going to be the negative magnitude at the point 1, negative 2. So let's recap kind of what we're saying. So we're at a point, the direction of greatest ascent is going to be simply what is it called? I'm blanking here for a second. Simply the gradient at that point. And again, that's because if I scroll back up for a second, we know that we want to go in the direction of greatest ascent. That means that u and the gradient of f are in the same direction, which is of course what we have when the cosine of the angle between them is 1. So we get this. If this is clear, sorry that I'm going over it, just want to make it extra clear, just to make sure it makes sense. And then in the opposite case, we just have a negative. So we have here is this. This is what we have. Now we just have to go ahead and compute it real quick, and then we'll be done with this question. Okay, so I'm going to scroll. Actually, I'll keep it right here for a second. So all we really need to do is calculate the gradient of f. And so we'll do this in black. Let's see. So the gradient of f at a point xy is going to be partial derivative of this function with respect to x. We get 2x plus 2. Now with respect to y, we get 4y plus 4. And so if we evaluate this at the point of interest, which is 1, negative 2, we get, plug in 1 for x, and then negative 2 for y. And what we get is 4, and then minus 4. So this is going to be the direction of greatest descent. This is our first answer in part 1. Direction of greatest descent. And then what we're going to get for the value is going to be the magnitude of this derivative. Sorry, magnitude of this gradient vector. And so what we get is, take the magnitude of the vector 4 minus 4. We get 4 squared plus minus 4 squared. It's going to be the square root of 16 plus 16, square root of 32. Again, 32 is 16 times 2. So we get 4 root 2. This is going to be our value of greatest ascent. Oops, sorry. So these are our answers for part 1. I'm not going to write it out for part 2 because all you have to do actually is just stick a negative in front of either the vector or just the number for the value. So that's going to be it for that. So we'll go ahead and move on to our next topic, which is going to be, again, another application of the gradient vector. One that I find kind of interesting. It's going to be the tangent plane. So we're going to scroll down and get some new space going. So we're going to look at tangent planes. Again, it might seem kind of like random, like I'm jumping between a bunch of different things, but not really that random because all we're looking at is applications of directional derivatives. And actually what I'm going to do is go ahead and move, whoops, did not mean to do that. I'm still learning. I'm going to go ahead and take this, move it down a little bit. Right there should be good. Okay. So what we're going to do is look at a little bit of geometry real quick. So we're going to start with a function pretty much like always. So what we're going to do is suppose we have some function of 2 variables, so z equals f of xy. That's all we have so far, just a function of 2 variables. Now, what we're going to do is a little bit of math trickery of sorts. What we're going to do is define a new function of 3 variables, capital F of x, y, and z. And we're going to set it, well, look at that in a second. So we're going to define a new function by subtracting f. By subtracting z. So what we get when we do that is we get that f, x, y, z equals 0. So we can recall from our knowledge of level surfaces is that this is going to be, since we have a function equal to a number, a constant number. It's going to be the level surface of some graph. But we notice that this function has 3 inputs. Whose output is going to be like some number, typically w, and it's going to be in 4-dimensional space. And so we can't really visualize that, but we know this is just some level surface of a 4-dimensional object. Okay, so let's look at an example of what I mean by this whole process I just kind of drew up. I'll keep the red one. So basically, for an example, what we could have is maybe the function z equals f of xy equals something simple, 2x plus y. And then to create the function f, capital F that is, all we're going to do is subtract z. And so we get 2x plus y. So looking up at the first one, if I subtract z, then what I get on the leftmost side is 0. Right, so it's an equivalent way of writing what I wrote above. So each point x, y, and z that satisfies this first set of equations will satisfy this one, number 2. And so we're going to continue on from here. Let's see. So I'm going to scroll down just a little bit. So we have some function, and we're going to define a new function, capital F. So what we're going to do now is let x equal x of t, y equal y of t, and z equals z of t. That is to say, each of my points is going to be described parametrically. So let these be defined parametrically. Excuse me. Parametrically. And so let's get a visual going before I scroll down and we lose all the stuff that we have. So what we have essentially is this. We have a level surface of an object, 4-dimensional space. So it's going to be something like this. And then what we have on this is a parametrically defined curve, right? Because x, y, and z parametrically defined. So when I plug in different values of t, I'm going to get different values in space, different points along this curve. C. And so again, C is just the path determined by this parametrization. And then what I want to look at is, well, let's come back to this drawing in just a second. What I'll do for the time being is just give it a name. This is going to be z equals f of xy. And again, we have x, y. So we'll come back to this guy in a second. But for now, what we have is, again, we had f of x, y, and z. But instead of that, I'm going to write x of t, y of t, and z of t. And this is going to be the function evaluated along this parameterization. So I apologize. I think this right here should be c. So this will be my curve c. So what this is going to be equal to, of course, we had on the right-hand side was 0. Scroll down for just a moment. And so what I can do right here is take the derivative with respect to t at both sides of this, dt, in which case, as you recall from before, we'll get the chain rule. So we get partial derivative of f, big F again, with respect to x, times dx dt, plus partial derivative of f with respect to y, times dy dt, plus the partial derivative of f with respect to z, times dz dt. And again, this is going to be the case because we have this specific tree diagram. We have f as a function of x, y, and z. And x, y, and z are all in turn functions of t. This is going to be 0 because the derivative of the right-hand side is going to be 0. And so what this gives us is that Well, what we have here is a dot product, right? Because each term that we have is two things being multiplied together. So all this really is the dot product of the vector fx, fy, fz, all these partial derivatives. So be thinking about what this is. Dotted with dx dt, which is x prime of t, times y prime of t. Sorry, not times, but in the next component, y prime of t. And then z prime of t equals 0. So what we have is a dot product of two vectors giving me 0. So what I know from this is that I have the gradient of f dotted with r prime of t is equal 0. And so in particular, at the time t is equal to t naught, what I have is that the gradient of f, well, if t is going to be t naught, then I'm going to say, let's see how I do it here. X of t naught, we'll call that x naught. Same for y. Whoops, sorry. Y of t naught equals y naught. Z t naught equals z naught. So what we're going to get is f evaluated at this point right here, dotted with this tangent vector r of t naught equals 0. So at this point, you might be a little bit confused. So what we just did was a lot, but it should be a little bit of solace to know that none of this stuff is new information. All we're doing is taking what we previously learned and applying it. So no new definitions here, right? All we had was gradient vector, we did chain rule, we looked at dot product. And so what I'm going to do is update the picture that I have. And so if I look, right, at this picture right here, and I'm going to be at some point P along the curve, then I know that my tangent vector is going to be right here. It's going to be r prime t naught. And then what I know is that what's perpendicular to that is the gradient, right? So this piece of information right here is actually really important. So what it tells me is that what makes a right angle with this is going to be the gradient at this point. So what I get is this sort of vector here that's making a right angle with this, and so it's going to be normal to this curve. This is actually a really big takeaway, but I'll summarize this here below. So we're almost getting to tangent planes. Hopefully this stuff makes sense, everything I've just written down, and not just think about it. Again, that might not even help, but again, if things don't help, you can always come into peer tutoring. We're located at the bottom in the library. Anyway, takeaways from this. Are going to be as follows. So first thing, I'll do a different color. Let's do black. My first takeaway is going to be that the gradient of capital F is orthogonal to the tangent vector at the point t naught to any curve C that passes through P on the surface S. And moreover, to surface S, guess we erase that guy. Anyway, surface S, and must be orthogonal to S. So again, we'll scroll up here just a second. This is going to be my surface S. The function z equals f of xy. And so we have this little red curve on it, C. And at a point we have this tangent vector. And so the normal to it, normal to the surface F, is going to be the gradient of F. That's this guy right here. Okay, so what we get also is that the most important thing I think from here is that the normal vector to a surface is its gradient. So breaking this down, so the surface is just going to be the graph of the function. So the surface is created by some function f. We can find the gradient of that by taking the partial derivatives, and then that turns out to be the normal vector at any point, which is super useful because when we want to find tangent planes, again, we define planes by looking at normal vectors, and so we're going to get the equation of the plane by looking at the normal vector that is the gradient, right? And that's going to be useful for us because we use tangent plane approximations. It's going to be very useful when we want to do more of the application side of things. So I might have been lying. So I think actually the most important thing, so I'll give it 2 stars. First one doesn't get any stars, but it's okay. We get that the tangent plane. So our tangent plane equation is going to be given by a little bit. So the tangent plane equation is going to be given by what we have typically is a normal vector dotted with the vector of any point on the plane. And so what we get is the gradient of capital F, the function we created, at the point x naught, y naught, 0 naught, dotted with the vector x minus x naught, y minus y naught, z minus z naught, equals 0. And this should make sense that the point x naught, y naught, and 0 naught is on the surface. That's what we defined before, right? We evaluated capital F along this parametrization right here to get a curve that's embedded in my surface. And so, of course, it's going to be on the surface S. And so just basically all that to say that this formula hopefully makes some sort of intuitive sense for us. Okay, so let's look at an example. It's always good to get some practice in with this stuff. So what we're going to get is an example. Okay, so what we're going to do is find equations of the tangent plane. So find the equations of the tangent plane and normal line to the surface x plus y plus z equals 6e to the x, y, z at the point 0, 0, 6. Okay, so let's take a look at what we have here. So we have 2 functions that are in R4, or 4-dimensional space, and we have their intersection, so wherever they're equal to each other. And so like when we take the intersection of 2 functions, like say for example in R2, like if I take 2 like equations of lines, and if they intersect, let's say where the intersection is not like, infinitely many solutions, they intersect at one point. And so basically all this is to say is when you have 2 intersections of functions in some space, their intersection is going to be 1 dimension less than them. And so what we're going to have is some graph in 3-dimensional space. And again, what we're going to do is start by naming what we have. So what we have here is this point's going to be x naught, y naught, 0 naught. So we're going to start here. And so what we're going to get is that, let's go ahead and start by creating our function capital F of x, y, z. It's going to be, what we can do is take x plus y plus z minus 6 times e to the x, y, z. Of course, this will be equal to 0. And then what we do is we take the gradient of this function, capital F. What we get is, if we take the partial derivative of f with respect to x, we get 1 minus 6yz e to the x, y, z. We get something similar for the second one. Partial derivative of f with respect to y is 1 minus 6xz e to the x, y, z. The last one's going to be 1 minus 6xy e to the x, y, z. Okay, so this is going to be our gradient. And so we want this at the specific point, x naught, y naught, and z naught, which is going to be the point 0, 0, 6. And so what we get is actually something really nice, because since x and y are both 0, in each of these right here on the right either has an x or a y multiplying it. Then what we get is all of them go to 0. So we get 1, 1, 1. So just the ones that are hanging out front. And so we're actually pretty much almost done. And so what we need to do to get the equation of the plane, again, we take the dot product of the gradient at a point with a point on the plane. And so we end up by saying that the gradient of f at 0, 0, 6 dotted with, now we're going to get x minus x naught. Maybe I could do this first. So we'll say x naught, y naught, z naught times this right here. This is going to be the equation that we have, equals 0. And so what we get is the vector 1, 1, 1 times x minus x naught. So again, x naught, y naught, z naught. So we get x minus 0, y minus 0, z minus 6, 0. So we take the dot product of 1, 1, 1. I should have been writing these as vectors all along. So we're going to do that now. Dotted with x, y, z minus 6 should give us 0. Right? And so what we get is x plus y plus z minus 6 gives us 0. So x plus y plus z equals 6. So this is going to be the equation of the tangent plane to the surface at this point. Okay, now we're still up to the second part, finding the normal line. And again, the way that we can do that is by first recalling that to find the equation of a line, what we need are two things, right? We need a point on the line, and two, we need a direction vector. Okay, so the line that we're looking at is the normal line, so it's going to be in the same direction as the normal vector, that is our gradient. And so what we have in a general sense is this following equation for a normal line. We have L of t. This again is going to be the parameterization of it. We get x naught, y naught, z naught plus t times the normal vector, which is going to be the gradient of f at this point, x naught, y naught, z naught. So in our case, so here we get that our normal line will be given by the point, of course, x naught, y naught, z naught is 0, 0, 6 that we've determined, plus t times the vector 1, 1, 1. And of course, this is going to be the case where t is any real number. So for every real number t. Okay, so now you can see on this same screen the equation of our tangent line. And, sorry, not tangent line, tangent plane rather, and normal line. So very useful applications of the gradient. So our normal line. So we're going to do one last thing, and this video is getting kind of long. Then after that, we'll wrap it up and call it a day. Last thing we have is going to be another sort of geometrically kind of based thing. And we're going to be looking at what we call the angle of inclination. Okay, so basically the idea is, so when we had like a line, right, when we first started learning about functions like many years ago, we wanted to know the slope of the line, right? Change in y over change in x. We wanted to know, for example, if I'm walking up this mountain, if I walk forward a little bit, how much do I walk up, right? And so we wanted to kind of generalize this. We'll maybe just talk about it in three-dimensional space by looking at kind of the angle of planes. And so what we have is something like this. So we have x, y, and z. And we want to look at something linear, which in three-dimensional space could be a line. But, we're also interested in planes as well, so that's what we're going to look at here. And so, maybe let's give this a little bit of tilt just to kind of emphasize what I want to do. And so we want to know, like, what is the angle or the slope for this plane, right? And so a way we could do that is by, we have to look at some vectors. Sorry, voice crack. So we have to look at some vectors. And so what we could do is look at this vector here. Whoops. We could look at the k vector that's going in the direction of z. And we could look at this normal vector, this plane, which we know is going to be the gradient, capital F, the function we create. And the reason we're doing this with k in the z direction is because when we look at the slope of something, we always compare the ratio of our output to our inputs, right? Like change in y over change in x, the y is our output, so it's going to be on top. So that's what we look at here. And so we can kind of take these two guys right here and look at them. We want to find basically the angle between these two. So we can move these vectors around and still get the same thing. So we get k right here. Then we get the gradient of f. And basically what we want to know is this angle between them, which we'll call q. And so basically what we have from our equations is we know that the gradient of f dotted with k, we've seen this a couple times before, is going to be the magnitude of the magnitude of the gradient of f times the magnitude of k times the cosine of the angle between them, which we just called q. Again, we are going to kind of do what we always do, say that this vector is of unit length, is length 1, so we're not going to even consider it. So what we're going to get is that this dot product here is going to be the magnitude of the gradient, capital F, times cosine of q. And so what this means is the cosine of q is going to be, let's see what we get here. We're going to get, what we do is we typically take the absolute value just to make sure we get the positive. So we're going to get is the gradient of f at some point x naught, y naught, z naught, dotted with k, all over. Now we're going to divide by the magnitude of the gradient at this point. So to find the specific angle then, what you would do is just take the inverse cosine of all this stuff right here. Okay, so let's do one last question, and then we will be done for the day. Alright, so our question is going to be, find the angle of inclination of x squared over 4 plus y squared over 4 plus z squared over 8 equals 1 at the point 1, 1, 2. So to find the angle of inclination, we're going to be needing a couple things. First thing we need is the gradient of capital F at 1, 1, 2. So the gradient of F is going to be simply 1/2 x squared, 1/2 y squared, 1/4, not squared, x, and then y, and then we're going to get is 1/4 z, evaluated at the point 1, 1, 2. So we get a half, and a half. What we also need is now that we have that, we can calculate the numerator of what we needed. So we're going to get this vector, a half, a half, a half. Now we're going to take the dot product of it with the vector k, so 0, 0, 1. Again, this is what we had right here on top. So go ahead and take a look at that for a second. Okay, now that we have that, basically what this is going to do, this dot product, is going to extract the last component. So we get absolute value of a half, which is, of course, hopefully a half. And then the last thing that we need, so we're good here. Last thing we need to compute is just the magnitude of the gradient, and then we'll be done. So we have our gradient right here. So we're going to compute its magnitude. So how about we say lastly? So the magnitude of this, 0.112, is going to be square root of, we have 3 half squares. So we get 3 times 1/2 squared. And that is going to be square root of 3 times 1/4, square root of 3/4, which we can write as square root of 3 over 2. So what we get is that the cosine of the angle between them, this angle of inclination that we have, is going to be, let's see, this number 1/2 over this square root of 3 over 2. So we get 1/2 over root 3 over 2, which hopefully gives us, if I'm not mistaken, 1 over root 3. And so we conclude that Q, the angle of inclination, is the inverse cosine of 1 over root 3. We'll just leave it like that. So, good. So thank you for watching. I hope you've had a good time. Thank you, and have a good rest of your